Thanks everyone for taking the time out of your day to show up to this webinar. It's going to be a quick 30-minute or so webinar about how we take full advantage of the carbon design process and carbon printers at our company. So I'll give a brief intro on Sherpa Design, and then I'll introduce myself and the co-host. So Sherpa Design is a mechanical engineering services company in Portland, Oregon. The primary business is mechanical engineering, mechanical design. But in addition to that, we have a machine shop with a few CNCs, a carbon 3D printing lab, and then NX CAD training and team center services. So I'm Connor Shimamoto. I'm the additive manufacturing specialist here at Sherpa. I have about 4 to 5 years of polymer additive manufacturing and design experience. And then we also have our co-host here, Sam Backus.
Yeah, Sam Backus, lead industrial designer at Sherpa. I moved to the Portland area about 1.5 years ago from Bay Area, where I worked in consumer electronics for 6 years with an emphasis on augmented reality and virtual reality. So I am Sherpa's first full-time industrial designer. And yeah, it's a pleasure to be here co-hosting today.
Yeah, and Sam's actually one of the people I work pretty closely with on quite a few projects. So he's got a lot of experience kind of going through this same process that we hope to carry out with more of our customers. So typically with traditional manufacturing, there's a few key themes. The timeline is usually measured by weeks. Design for change is somewhat limited. There's a lot of prediction involved. One of the key benefits, though, is just the ability to scale up into massive quantities. And then a few key themes with additive manufacturing is that the timeline is typically measured by the hour or the day. It's really easy to iterate fast, and qualification can happen during the process. A lot of times we'll just be prototyping, and eventually we'll get to a part that feels like it's the one. And that will actually go straight into production without really any delays. One of the drawbacks is that it can be a bit more challenging to move up into the higher quantities. So usually if the quantities are in the 5-digit range, for our shop at least, that's where we tend to look back at traditional manufacturing, like injection molding. But yeah, with additive manufacturing, it's super fast to just kind of keep parts going as you're making updates in CAD. One of our engineers described it as being kind of similar to agile manufacturing. He said it's kind of like he's designing with the expectation for something to change, and just do continual rollouts versus one big update and then leading up into it taking weeks or months of planning. So at Sherpa, one of my keys to success is early involvement. Whenever there's a new project that comes through the door, I try to start asking questions right away. I just ask about the quantities. Is it a consumer product, R&D, what industry it might be in? The chances of success are always better when I get involved early on. And that's for a couple of reasons. I think it lets me think about design for additive manufacturing a little bit better. And then it also helps me pick out the materials and also, I guess, just define how we're going to work as a team, and just have the expectation to be prototyping constantly.
To add to that, so at least internally, when we're working on parts that we're using for prototyping or that we're planning on making in larger quantities, early involvement is best because it means that we're going to be working collaboratively with our 3D printing department. So that presents us an opportunity not only to relay what the specific project requirements are, but also introduce a little bit of that design thinking to create empathy and kind of understand the user and the end use case. And so we can kind of proactively start solving problems or address issues, and from the get-go, design with additive manufacturing in mind.
Mm-hmm. Yeah, and when people like Sam started, they hadn't had a ton of experience with this specific printing process. So when we had early involvement with one of his first projects, he was actually able to learn about the process of printing and cleaning and curing post-processing as we went along. So that I think that contributed a lot to the way he was able to design parts better for printing. Whereas later involvement I feel like I kind of have to go back and kind of reteach things. So once we've identified a project that maybe has some potential in it, I take a closer look and really try to identify application of the printer. So first, I'll look for parts made of plastic. It's kind of like the low-hanging fruit. Um, Parts made with other materials that could be replaced with plastics off the printer. So sometimes aluminum machine parts might be a little bit too much. And it turns out some of these printed parts can be a suitable replacement. Parts with consolidation potential. So if I see a handful of plastic parts that maybe are broken up into multiple parts due to manufacturing constraints, I'll see if there's a way to print it all as one piece. And then last but not least, I'll identify unique design challenges. This is kind of my favorite. If there's something that just seems a bit more vague and abstract in the beginning of the design process, I try to see if there's a way we can print a solution. And then here's an example of that unique design challenge. It's actually an end effector. So we were tasked with making a automated manufacturing machine, and it required a set of end effectors that would pick up a part, move it around this machine, and hold it during a couple operations. The challenge was that the parts that we were picking up had some variance in shape, density, and they also needed to be gripped on at the same time without crushing the part. So we actually just kind of sat down and just shot out crazy ideas. I didn't really have a specific route that I wanted to chase immediately. It was just about being abstract and just not being afraid to try, especially with the printers in house. It was really easy to just start printing things. So we threw out the idea of a toothbrush. Can those bristles be used to hold parts more effectively? It's compliant, it's delicate, and you could shape the bristles to conform to the parts that you're holding. So you could kind of see the progression of this part. All the way on the left, that's the first prototype, and then third from right is the production model that we're currently using. And then the last two in the rows are just some R&D that we've been doing since. Just because we found a suitable part didn't mean that we were kind of done developing. So we just kind of tried to see where we can take this. So yeah, this is kind of a recap of more of those parts on the right. The top set, that's the current production model. It did require a few supports. As a result, the tolerances were a bit looser. The surface with the supports on it was a bit rippled. So I decided that that's going to be the first thing I tackle. How can I get rid of those supports? So more towards the center, I was able to make a support-free version. Instead of using an annular snap fit, it just slid on. So that made it a shorter print with fewer handling steps and a more consistent fit, and just an overall lower cost. And then at the very bottom, I tried latticing this part. I assumed it would be more compliant, save resin, and save time. And ultimately, that led to a potentially lower cost. So hopefully, when we do the next rollout of this product, we can implement one of the two designs at the bottom.
And just to follow up on that, that the quantities of these parts being produced at going with traditional manufacturing processes like casting or injection molding for this would have been much more expensive, and we wouldn't have been able to iterate in quite the same way. And with this, by the time we got to our second R&D concept, this is not manufacturable with any other manufacturing process, and most other printers can't produce lattices this fine in detail.
Mm-hmm.
So the carbon printers really enable us to not only to pursue more creative solutions because they print really quickly, but they also print in much finer detail and much higher quality than most other printers do.
Yeah, the elastics that come off the carbon printers, we found them to be better than most on the market. Tear strength is great. They're really isotropic, and they could handle a ton of cycles. Like these parts had been cycled thousands and thousands of times without any degradation. I don't even think I've had to replace one of them off the manufacturing machines. And then after we found an application or a challenge, I make sure to go through a few criteria. I think this step's important to make sure that we don't set ourselves up for failure later on in the process. So the first of the three requirements is that it has a suitable material. So I just need to make sure the carbon resins can hold up to the environmental factors. Is it biocompatible enough? Things like that. And then next is manufacturability. I don't want to try to move forward with a part that's impossible or challenging to manufacture. So I just make sure it conforms to the general guidelines of the carbon printers, wall thickness, height, does it fit in the build platform? And then also I like to consider how much post-processing is required. Less is better. And if we determine this early on, if there is a lot of processing involved, we could at least try to troubleshoot that and find ways to design the part differently or just improve our processes. And then the next is value. The value can be a monetary number, or it could just be a performance issue. So yeah, one of the things with additive manufacturing is it's a lot easier to get started up. There's less upfront cost. It's a lot faster to put parts into the market. And then also just the value of being able to prototype and then move straight to production without really any delays. So here's a good first example. I think this might have been our first production part. It's a replacement part for an aviation headset. So this was by a small business that repaired pretty high-end aviation headsets. He was noticing this one part was constantly failing, and it was difficult to get replacement parts from the OEM. So they actually reached out to us and sent us the original part. They didn't have any CAD, so we had to reverse engineer and basically rebuild this part so that it could be printed. So for their material requirements, it needed to withstand up to 55°C. I believe that's the same temperature as a hot airplane or helicopter cockpit on a summer day. We actually didn't find this out until later in the process, but luckily we were able to respond quickly to the problem. And then manufacturability. This was a great part to print and manufacture on our machines. We could print a lot at a time. It was almost entirely self-supporting. The supports weren't on any mating surfaces, so we didn't have to remove them. They weren't on cosmetic surfaces either. It was compatible with our smart part washer, and it did not require salt baking. So for those familiar with the carbon printing process, a lot of the rigid resins benefit from baking in a big tub of salt. It just minimizes warp, but it's also a little bit of extra time. So we were able to get rid of that step. And then the value. The part was designed for injection molding originally, and we think that was the source of some of the failures. So with carbon's printers, we were able to design differently and minimize those failures. It was also very low initial cost. The small business didn't want to commit to the high upfront cost of injection molding. With us, he was able to minimize that. It was probably 10 times less than it would have been to mold up front. And then he was able to make these on demand too. We can make as low as 50 at a time without really having any hiccups. With injection molding, he would have had to forecast a little bit more and probably order higher quantities. And it was a safe bet for him too, because he wasn't sure what his quantities would be in the first or the second or the third year. He was just able to respond basically on the week. And then we were able to make design changes as we went along. The first version wasn't perfect, so we just kind of continually made improvements as things came up. So here's a bit of that process. In the top left, that's us 3D scanning the part. And the top right, that's a bit of reverse engineering that we did in NX. And then on the bottom left, we just validated the part. We're just doing a quick overhang check, but we're trying to see where the supports might be required. Are there regions that we could design self-supporting features into? And then on the bottom right, that's the actual manufacturing. So that's right after one of our technicians washed the part. You can see that there's 12 parts per platform. It's roughly a 2-hour print, and then the next day we have a bunch of injection mold quality parts. So here's a quick lineup of just that progression and those iterations. Then I'll go into a little bit more detail. This was the first print. It was just raw scan data. We hadn't done anything. It was mostly just a sanity check to make sure this thing was scanning in at the right scale, roughly the right shape and size. The holes weren't really the right size or depth, and surfaces that were supposed to be flat weren't exactly flat. So it made printing a bit more challenging and time consuming. So for the first production version, we flattened out what was supposed to be flat. We corrected all the holes to be the correct diameter and the depth. But what we did notice was that it was difficult to clean. It was really inconsistent. At this point, we might have not even had our smart part washer. So our yield rates weren't really perfect. You could see in the photo that there's some kind of like goopiness. That's actually an example of kind of the worst of resin not being perfectly cleaned out. And then we still experienced a few fractures. He would call us up saying, one person broke a part here or here and send a couple of pictures. And we realized that all of those fractures were right where the injection molding features were. So there's a few voids, and we are pretty sure it was for sink prevention. So on this part, we got rid of those injection molding features. We just solidified the area. It made printing smoother, less supports, and easier, more consistent cleaning. So what we saw was improved yield rates, less cases of fracturing, but it still required baking and salt. It was about an extra 20 to 40 minutes per day. But we didn't think it was a huge deal. And then occasional cleaning defects. At the top left, you can see a tiny bit of that goopiness or fuzziness. So this current version that we're actually printing right now, we had to change it to a new resin. We changed it to the EPX82 resin. The customer called me up saying that a lot of these were warping over time, and we realized it's because summer was rolling around. So we switched to EPX82 for the higher heat deflection temperature. And we also realized a couple other benefits as we switched over. It cleaned much better in our parts washer, really consistently. And then the yield rates were pretty much 100%. I don't even think we broke any during the printing or cleaning process. And then also he noticed less cases of fracturing from his customers. And then also another thing we noticed is that the parts were possible to bake without that salt. We were able to just put them on a baking rack and get accurate parts. So this was a great story of kind of iterating as we went along and tackling problems as they came up. And then here's another example of another good fit. I think it was kind of on a different end from that last part. It's a bit more complicated, a bit larger, definitely a higher cost, but the value factor was higher. So for materials, the first requirement was surviving temperatures up to 80°C. This is a power supply fan duct, so it's in a small metal box with a lot of heat generation. It also needed to pass some military standard testing. There's chances of these being used in pretty harsh environments, so it actually went through a lot of shock, vibration, and environment testing, and actually performed great and passed everything. And manufacturability, same thing as the last one, almost entirely self-supporting, and the supports that were there were on non-mating, non-cosmetic faces. It was also part washer compatible. One thing with this is the print times per part were actually much longer. We could only do 2 at a time. It takes roughly 3 hours. So that was a bit of a setback, but we realized that the value outweighed that by far. So we evaluated this for machining and molding at one point, and it was just too complicated. We would have had to break it up into multiple parts, sacrifice a lot of performance, and it would have slowed down our entire design process too. So time to market was much faster. And then also we were able to tackle design updates kind of as problems came up. I think we only had to make one revision. But yeah, relatively smooth to get this into manufacturing. And then same thing, we could order these on demand. So if the customer came to us with an order for 50, great, we can make those. If demand changed and they wanted 300, we could definitely tackle that, and it didn't really seem to affect us at all. And then now we're kind of getting into some of the thought processes or ideas that kind of keep us creative and just constantly exploring at Sherpa. We're always looking for new tools that we could integrate with other processes. Here's an example of a part that I 3D scanned. I used NX to reverse engineer it. And then I actually used Rhino and Grasshopper to do some lightweighting. And then we actually took that and brought it back into NX to finish off a few last design details. And when we don't get presented with a problem at Sherpa that forces us to explore other tool sets, we actually just make up our own. So here's a picture of our summer intern. He had an interest in custom earbuds. So I told him to just go for it and make his own using all the tools we had at the company. So in his 2 to 3 months here, he learned how to mold his ears, 3D scan, modify those 3D scans, and then print them. So you could kind of see the progression in parts. And also on the CAD side, he went from not knowing any NX to kind of becoming our expert at scanning and manipulating that scan data. And here's an example from one of my projects. I do a lot of biking, if you haven't noticed, on Sherpa's website, but it's my greatest excuse to just get creative around here. Every time we get a new tool or I have a little bit of downtime, I'm just looking for ways to print my own bike parts. So here I'm taking a 3D scan of the lower section of my bike, and instead of doing a bunch of hand measurements to make sure the parts fit, I just built the part in CAD right over the scan data.
Yeah, and at Sherpa, whenever we have new materials come in for the carbon printers, or we have new tools at our disposal, we always try to find new ways of using them or creative ways of using them. We got a fireproof or flame retardant material in a couple months ago, and so we were able to print some parts and set them on fire, which was obviously a pretty fun exercise, but it also let us know what the design limitations of the material were.
Mm-hmm. Yeah, it's kind of an expectation on my team, at least, that when a new tool comes in, we better be looking at it and thinking of ways to bring it into our process. Everybody should be making something at all times. And I think that's probably the great benefit about working at Sherpa. And then this is our last section. It's about ideation and creativity. I think this is one of the key factors to us kind of staying on top of the game and just constantly coming up with great ways to use the printers. To us, ideation is basically just coming up with a bunch of new ideas, just being unfiltered and just trying new things. Typically, our medium is just drawing or written notes. Document as much as possible. The goal is just to go beyond what's already out there, exceed the precedent, explore a lot of options.
Yeah,
I
and
try to think of. Oh, go ahead.
no worries. So Connor and I both have degrees in industrial design, and so we both are bringing that design thinking into this. So like I said earlier in the presentation, part of it is the hardcore industrial design skills like sketching, being able to collaborate, bounce ideas off each other, and really think in these blue sky terms where we're really like thinking about like things that maybe are stretching the limit of what's possible, and over time whittling that down into 2 or 3 concepts that are viable, realistic, and that we can try out. And then with those concepts, we can move forward, test them out. And once we're done testing them, then we can find out what the ultimate concept is, or what can go into production. Working off of parts we've developed internally, Connor and I have had many sessions where we're sitting in front of a whiteboard, just drawing, coming up with ideas. Some of them are ridiculous, and that's totally okay. And then when we test them out, we actually have some really unique findings. I'm not sure if I can talk about it too much, Connor, but we developed a modular system for these little soft, basically like cushion parts. And so based on the design that I was pursuing at the time, there's so many moving pieces in this at the time that we didn't want to get stuck with one solution and have to constantly redesign that. So Connor and I came up with a system that was much more modular. And so as the rest of the product developed, we were able to keep this one piece the same and make small iterations on it. And now that the rest of that product is much more mature, we're able to take that modular system and turn it into something that's more specialized. But in between, we were able to come up with a really smart solution to allow that to go on the back burner for a while and be a solid foundation to build the rest of the product off of.
Yeah, and that was just a great product of kind of like this ideation process. It was really just like a random idea I had one day. And I just tried it. I just made the part, and it turned out to lead into a lot of great things. And one thing that I try to do with this whole kind of like brainstorming process is just uh, I try to use manufacturing as more of an opportunity than a limiter. I think a lot of times there's a habit of thinking of manufacturing processes as like restrictions of things you can't do, but we try to think of it the opposite way. And yeah, the process is not always linear. Um, we try to start broad, start really crazy, and then narrow down. And a lot of times we'll even loop back around just to check and see if there's something that we might have missed along the first pass. Here's just a quick workflow that Sam actually illustrated here. It's kind of how we work at Sherpa and how we get through design problems and just the entire product development process and how we bring in the 3D printing with the carbons.
Yeah, and this is a pretty typical chart of what the design thinking process looks like. But I think one of the big things is in the middle, there's the area where it's ideate and refine, and then there's this loop between concept and prototype. And so, Connor and I collaborating on parts, this is kind of where we come up with a lot of ideas, we prove things out. We try a lot of things, and some of them end up with like completely unexpected results, and some of them are just downright funny. But every now and then, what starts off as kind of a ridiculous idea, or an idea that we're not sure if it'll work or not, actually ends up being a pretty golden concept, and we can end up moving that into the final design. And one of the big things that the carbon printers really enable us as a tool to do things that I don't think we'd be able to do with most printing processes. A lot of other printers I've used in the past have a lot of pretty strict design criteria, and the quality is questionable. It requires a lot of post-processing, and I feel like with the carbons, we have a much different scenario where we can create a prototype, and with just a little bit of refinement, we can really make it shine as looking like a production part.
Mm-hmm. Yeah, it almost feels like we're doing the development process and prototyping with production quality parts. And it's nice to know that things won't change once you do scale up. And then to bounce off of Sam's comments about just coming up with a lot of crazy ideas and trying them, and some of them being pretty novel but not really useful. A lot of those I document and keep in the back of my head and just see if it'll come up useful in another project. So all the extras or the cool findings that aren't really applicable, they actually come in handy later on. And that brings us to the end of the webinar. Thank you.
Yeah, thanks guys. It's been a real pleasure to talk to all of you, and yeah, reach out to us on the Sherpa website or LinkedIn.